all the y values in L2. I wanted to use a little shortcut to get the x values in there. So the first thing I would do if I were you is make a clear, definitive statement about how you're creating a scale. If you, assuming you're not putting in 1945, 1950, and so on. The overall theme here is the number of people living on American farms has steadily declined in the last 70 years. If you actually put in 1945, you're establishing zero as being the year zero. Right? So there's a whole lot of time elapsed that would be completely irrelevant to the situation. Right? So what I'm going to do is I'm going to let zero be 1945. All right, so that would be my baseline. All right, and then it appears that it's going by fives. You know, you just double check, make sure nothing skipped along the way. 55, 65, 70. It looks good. All right, so this would be zero. I mean, you wouldn't have to label it here, but you know, once you define the variable, well, it's not a variable, but when you define the characteristics of the x variable, then you know things kind of are assumed after that. You wouldn't have to explicitly state it. All right, but 15, I'm just going to write it anyway. 20, 25, 30, 35, 40, 45. All right. So in my L1, I want to go from 0 to 45 by fives. So second, stat, ops 5. I mean, unless you want to just type it all in. But the expression would be x, with the variable being x. There's actually two ways to do it. You can make your expression 5x, right? Whatever x is multiplied by 5, that gives you multiples of 5, bless you. Starting with, let's see, this would be 0 to 9, it looks like. You can do it that way, or you can go xx, start with 0, end with 45, and go by 5s.
What did you click right before this?
Second stat, ops 5.
Okay.
All right, so 0 to 45 by 5s. So I'm basically establishing a linear relationship. When they say expression, you know, it's really, it's kind of a catch-all, but we can actually think of it as an equation, all right, where y is equal to, like if you were to graph a function, f of x or y would be equal to whatever you want it to be. So I'm using y equals x, keeping it simple. But then I'm only considering every fifth x value along the way. So it's like, well, what would y be if x is 0? It would be 0. What would y be if x is equal to 5? It would be 5, then 10, and so on. All right, so you can do it that way, and it'll populate the entire list. All right, you just got to make sure that you counted right, because the number of items in L1 has to match the number of items in L2. All right, so that would be one way. If I wanted to go by 5s but using a different linear function, second stat, ops 5, let's say I wanted to do 5x, where the variable is x, I wouldn't go from 0 to 45. That would be pretty lengthy. All right. Even if I'd be going by 5s anyway, but it wouldn't give me the numbers I want. Right? Instead, I would go from 0 to 9, and the step would be 1. All right, so replace the expression, the x in the expression with a 0, you get a 0. Replace it with a 1, you get a 5. Replace it with a 2, you get a 10. And it'll populate the list for you. All right, but that opens the doorway to create a change in variables in any way we want, or a change in scale associated with the variable. All right, so I could go by units of pi if I want, right? Or I could go by a function. If I wanted to increase by some quadratic relationship or a logarithmic relationship, I can let my expression be the log of x. All right, so I can scale it in different ways. All right, but anyway, here it's just make a scatter plot. I mean, you could have typed all this stuff in, but remember, the scatter plot settings on your calculator should be there Like what you see on my screen right now should be what's in your calculator. If it's not, make it that way. All right. I would, if you have a calculator, I would do it now. If you don't, then make it a point to do it. All right. I'll paste this into the notes so you have it, but it should look just like this. All right. At least as an initial setting. I mean, maybe they're both off so that when you're in your pre-calc or calculus class or whatever, you're not looking at a scatter plot every time you're trying to graph a function. But we need it on now, so that's how it ought to be. All right. So again, you go in. If you need to set it up, very simple. The type should be a scatter plot for both of them, plot 1 and plot 2. It's list 1, list 2 for X list and Y list. Pick whatever mark you like. It's probably a good idea to choose a different mark for your residual plot, which would be plot 2. All right, so I'll make that change right now. I'll go with a plus sign. But it's still a scatter plot, just comparing L1 and resid. All right, so again, to get resid, we go second stat, right on down the line till you find the one that says resid. All right, that would be your residual plot. All right, I don't want to look at that just yet, but I want to have it set up and ready to go in the event that I do need it. All right. Now, when you go into y equals, you see plot 1 is turned on. If you're in your other class, your other math class, and you're like, man, I keep getting dim mismatch error. I don't know what's going on there. Just go in here and hit enter on plot 1. I know we've talked about this before, but it never hurts to talk about it as many times as I can, because it's one of those things where you don't experience the issue, so you don't think about it. You don't think about the relevance. But then you're sitting there in the middle of the AP, and you're like, what the heck is going on with my calculator, and I can't help you. All right, so the more times I mention it, I think the better. All right, but we want plot 1 on to look at the picture. Zoom 9. I mean, it doesn't look linear. It's got a curve to it. It looks logarithmic. Well, we could say logarithmic or exponential. They're inversely related. You can transform an exponential into a logarithm and so on. All right, so I mean, you could transform any function into any other function if you want, but it's just a question of what it would look like. So I'm looking at this. I got my scatter plot. I'll paste this in there and at some point. It looks great. Mission accomplished for number 1 or part 1 or part A, whatever. According to the regression equation, well, we got to figure that out because it says find the LSRL, least squares regression line. So stat calc 8. Yeah, Luke.
I just can't read what you have written to the left of 0.
Oh, this?
Oh, sorry.
Oh, yeah, let 0 equal the year 1945. All right, so stat calc, option 8. All right, really, all these regs that you see here, they're tempting to use. You look at it and say, oh, I got to do a cubic regression or a quadratic regression. And you're like, oh, there's one right here. That's not the way we're going to do it. All right, I'm going to show you how to do those other types of regressions in a few minutes. All right, so it has everything to do with the table that's on the next page. But linreg A plus bx, list 1, list 2, we always store it. It's a pain that we got to do this every time, but it is what it is. Store it into y1, calculate. You have your information. Right? So the equation here would be y hat. We use the appropriate notation. Right? It's not going to feel good when I take off credit for that on an assessment. Right? If you don't do the hat, it's like it seems weird. I mean, it's actually called y hat. It's the dumbest title for a variable ever, but you got to have your y hat there. So 31.493 plus, well, actually minus plus negative, so minus 0.587x. All right, so that's my linear regression model. The R value here says that this is a great fit. But context and the picture, the scatter plot, tells us something else. All right, so we look at the picture and it's like, oh yeah, it's going through most of the points, but it based on the situation, number of people living on American farms has steadily declined. Now, did it steadily decline in a linear fashion, or did it steadily decline in an exponential fashion? All right. You think about, I don't know how much you've done in the past with sequences and series. You should have done something with it in algebra 1, algebra 2. But, the idea that if you have a sequence of values, it could be what we call arithmetic, where you're just adding, you're following a linear relationship. You're just adding a constant value to each term to get the next one down the line. An example of that is what we just did in L1. We increased by 5 every step of the way. But you could also double. Like what if I wanted a sequence where I'm doubling every value or halving every value? The old example is when you have the bouncy ball and you drop the bouncy ball and it reaches, let's say, 75% of its original height on the first drop. Then it bounces again. After that, 75% of that new height, 75% of that new height, and so on until it comes to rest. Theoretically, it'll never come to rest. It'll always be a percent of its original height. But, practically speaking, it would come to rest. The ball will stop bouncing at some point. Right? But that's not a linear relationship. Right? They call it geometric, but it's really exponential. Right? It's synonymous. So in this case, we're looking at, it looks like kind of a percent decrease over time. All right? So just using your senses, you look at it and say, it doesn't feel linear. All right. According to the regression equation, how much did the farm population decline each year on average during this period? That's a question of slope. All right. So we have, again, the regression equation. All right. So declined at a rate of 0.587. Oh, I forgot. Little typo here. And honestly, I don't know what the answer is because I can't remember. But obviously, the population wasn't 32.1 people. Right? So it was either in thousands or in millions or something like that. Right? So something I lost in the shuffle here. So that's a typo for somebody. I would imagine that in 1990 we probably had more than 7,200 people living on American farms throughout the country, so it's probably in millions. All right, so I suppose it could be hundreds, thousands, and but the most likely one is that it's in millions. All right, so declined at a rate of 0.587 million per year. All right. The percent of observed variation in farm population is accounted for. What is that percent over in linear change over time? That's the measure of the R-squared value. So I'm just going to run the computation again. So 0.977, so 97.7%. All right. And so what that's telling us is it's a correlation measure, but I kind of call it in my mind anyway the lockstep factor. Right? So it's like if it's a 1, it means that all of the change in y can be explained by the changes in x. Right? It's a good step in the direction of causation. Right? It's establishing mathematically that there is such a relationship between the two variables that it's likely that one is causing the other to happen. All right, but the context determines that anyway. Pierce?
So variation always R-squared.
Yeah, percent of variation is always going to be R-squared. All right. So in this case, what's happening is we have some movement in y that's dependent on x, but it's not fully in lockstep. Right, I kind of visualize you got two people walking. One is a clone of the other. All right, but that person, that clone, is not quite the same size as the original person. All right, so it's 97.7% of the size of the original person. So you cloned it, you messed something up, you got a little mini me on your hands. Well, 97.7 is not that bad. All right, you lost a little bit. But if it's 2%, you could have like a little miniature, just kind of walking around with you. And so I look at it based off stride length. When the original individual takes a step, it's going to be of a certain length. The clone is also going to take a step, and it'll be a certain length. That length will be 97.7% of the length of the original person. Luke?
So I just don't understand, like, I get that, like, you put it into the linear, like, equation formula, but, like, how do you just, like, interpret that and understand, like, which R values you use?
For C?
Yeah.
Oh, yeah. So percent of variation is R squared. That's the definition. So it's kind of like, just memorize that fact. All right. So that is the same as R squared. All right. And we can predict. We have a regression model, so we can make a prediction based off of that regression model. So it's saying in 2010, well, 45 years got us to 1990, so we'd need to go another 10 years to get to 2000. So 20 years later, basically, after the 45, so 65, right? So I'm looking for y hat of 65. I'll throw an approximate there. Alpha trace y1. We stored our regression equation into y1, so that's ready to go. Pop in the 65, we have a negative number. And that's one of the issues when you have a decreasing linear function. You could get negatives. Right? So we're talking negative 6.648. All right? And we're assuming it's millions. Is this a reasonable result? Why? Well, no. Not a reasonable result. Because negative population doesn't make sense contextually. I mean, it's a classier way of saying you can't have a negative person. All right, so that's philosophical, I suppose. You decrease to a certain number of people over time, so you're losing people. If you get to a negative, you're losing negative people. So maybe that means you're gaining people now. All right, so it's now you're like what? Importing 6.648 million people on top of what, though? Like on top of 0 people or on top of some other number that we're not privy to? Right? So contextually, it doesn't factor in. Right? But that brings up an important piece of conversation related to practical domain, but also whether it's an appropriate type of function to use. Right? So that's where the residual plot comes into play. Right? So we go in to our y equals, we turn off plot 1, we turn off the equation. It really doesn't matter about turning off the equation. It's just unsightly, so I turn it off. Right? And then zoom 9 it again. And if you see a pattern in the residual plot, any pattern at all, doesn't have to be a particular pattern, it's indicating that a linear relationship is not appropriate. Right? So in this case, I'm looking at something that, it almost looks like a parabola. Right? You got a couple of straight points, but that happens even in the best of times. Right? So you collect raw data. Sometimes there's going to be, values that line up perfectly, and then there's going to be some values that fall off the beaten path. That's perfectly fine. All right? But if you kind of squint a little bit and ignore, okay, if you find yourself ignoring 7 values, then you're probably looking too hard for a pattern. But if you ignore 1 value, I'm just covering up that one on the lower, this bad boy right there, pretend that's not there. I'm looking at something that looks fairly parabolic, right? Doesn't mean that a parabola is the best fit model. It just means that a linear model is not appropriate here, right? So then we start thinking about, okay, well, what is appropriate? So then you think about the situation, right? You go back to the scatter plot. If you're evaluating this stuff correctly, you'll find yourself going back and forth between different plots, trying different regression models, and everything, just kind of fleshes itself out. Right? So Zoom 9, my first instinct said exponential logarithmic, something along those lines. Right? That's where my brain is taking me. Now you can make a case that this is part of a parabola. Is the population going to, and this is where the context comes into play, is the population going to decline, reach some sort of critical point, and just stay there? Or will it decline, reach some sort of critical point, like some, maybe 100 years down the line, and then start increasing again? I mean, you can make a case either way. Right? I mean, American farms. Well, we need produce, right? So, I mean, it can't go down to 0. I mean, things would be very problematic if it went down to 0. Right? If it gets down to some low number and then starts increasing again, maybe funding increases, something that allows for people to be enticed to join the farming community. I don't want to wake up at 4 o'clock in the morning to milk the cows, but like somebody might look at their current job and say, I'd rather milk cows at 4 o'clock in the morning. I don't know. So can it increase? Sure. Right. So what we'd have to do is determine or investigate the reasonableness of the situation. All right. So what does that mean? It really, unfortunately, or fortunately, depending on how much you like to do this stuff, it means doing B, C, and D all over again, just with a different function. So how do you come up with a different function? Well, I got a big juicy table here for you. That's pretty intimidating to look at. Right? But it boils down to a very straightforward concept. Right? So the idea is that what we want to do is linearize the function. Right? Because we have techniques that allow us to evaluate the reasonableness of a linear relationship, the residual plot. Right, determining R-squared values. So you look at something that may be nonlinear and ask yourself, is there a way that I can transform this into a linear relationship? Right? And so in this case, it's going to involve a suspicion, but I'm looking at a graph that looks exponential. Right? So I would make that assumption that it's an exponential relationship. I could also make a case for a logarithmic relationship. Right? So then we think about what is the general structure of an exponential. Because you have the rules here. It's wonderful. I mean, you look at it, it says the dependent variable is the log of y, but you kind of look at that and say, well, where's that coming from? Right? Especially if it's an exponential relationship, why would I use a log? If it's a log, why would I use an exponential? Like how does that work? So let's say we suspect it's exponential. All right. If it's an exponential relationship, it's going to follow a parent function that is exponential. It's just a question of what kind of exponential function you'd want to work with. All right? Because you could work with base 10 or base e. Right? Older calculators only had base 10, base e, but more modern calculators let you use whatever base you want. So you could do whatever you want. The AP folks tend to stick with the base 10 exponential function. So y equals 10 to the x power. But you could also work with y equals e to the x power. Right? Both of them are parent functions, but of different bases. So y is defined in terms of the explicit expression 10 to the x power, e to the x power. So if I know what x is, I can figure out what y is based off that relationship. All right. So what I would want to do is allow for a transformation so that my y values can be of this form. All right. So I need my x values to become powers of 10 or powers of e, depending on which way you do it. All right. So it's basically like, okay, solve for x. So how do you do it? You take a common log of both sides of the equation. That's one way. You could also convert into logarithmic form. But this is the preferred way. Not by me, by students. I show both ways, and they're like, all right, what was that other way that was much easier to understand? Can you do it that way? So I'm just jumping into it this way. All right, so you take the log of both sides. We know, well, hopefully, that we can apply the power rule for logarithms. You know, the exponent jumps over to log. I think Miss Hamilton would say the exponent jumps over to log like a frog. So if you ever had her, you might have heard that phrase before, or saying. Anyway, powers become coefficients, essentially. So we would say log of y is is equal to x times log of 10. All right. Now, log, or a common log, is a base 10 logarithm. So the log of 10, you know, maybe you don't know this, maybe you're a little rusty on your logs, but if you type that into your calculator, you'll get the right value. But whenever the base and the argument within a logarithm are the same, it cancels to 1. All right. So, but if you don't know, you type it in. Oh, look, it's a 1. Great. So x is equal to the log of y. All right. Same idea over here, where I would take, instead of a common log, I would take a natural log of both sides of the equation. Exponent jumps over to log like a frog. And we have natural log of y is equal to x ln e. Natural log of e, if you don't know, is 1. So we have x is equal to the natural log of y. All right. We say equal, but it also means relates to, or corresponds to, or correlates to. All right. So what we would do, if we want to transform this, or we call it linearize, right? It's a linear transformation. What we would do is take either the common log or the natural log of every entry in L2. All right. So, because that's the relationship. X corresponds to the log of y, all right, based off of these models. All right. So I'll use the common log. So log, I hit the wrong thing. Log of L2. So I just took the common log of every element in L2. All right? And what that actually means, just going back to this expression, the 10 to the x power, is these are the powers that 10 would have to be raised to in order to equal the entries in L2. So 10 to the 1.5065 power would give you a 32.1. 10 to the 1.4843 would give you a 30.5. So every entry in L3 is 10 raised to whatever that power is, right? So when we come up with this exponential regression, what we're saying here is it's not y equals a plus bx. It's the log of y is equal to a plus bx, right? Because we just transformed the variable y into the log of y, all right? So we would say, you know, again, under normal circumstances, it would be y hat is equal to a plus bx. I'm saying, okay, not that. It's really the log of y is equal to a plus bx. That would be the exponential transformation, all right? And that's what I mean by, in the column below where it says transformations, dependent variable is log of y. That's where the log of y is coming from. All right. So what we would do is run the regression on L1 and L3. All right. We changed the basis of the system. All right. So L1, L3 using a linear regression. All right. So stat calc 8. L1, L3, store it, all right, alpha trace y1, calculate, we're looking again at the r squared value to determine the fit, right? How, what percent of variation in x can be correlated or explained by changes in y and vice versa, right? In this case, log of y. But also we have an equation. We have something to work off of. All right, so I now know that the log of y, so log of y hat, would be equal to 1.5505, so 1.551, minus 0.0151x. All right. So then if I actually wanted to come up with the equation in ordinary terms, because this is an equation. When you're solving for y, ideally you'd have it just y alone. But if I say y squared is equal to 16, you say solve the equation, and I don't take the square root. I just leave it off at y squared is equal to 16. I'm still telling you a true sentence. I'm telling you something that relates the value of y to a particular number. I just didn't simplify it enough. All right? That's what's happening here. We have a relationship between y hat and x. We just haven't simplified it to make it explicit. All right? So log of y hat is equal to this, which is wonderful. But I would have to convert it back into exponential form, because again, we have that understood base of 10. I'd have to convert it back into exponential form in order to establish the value of y hat. All right? So it would become, the circular motion, raise the 10 to whatever's on this side and set it equal to the y hat. Those log skills that you learned and didn't really do a whole heck of a lot with, they come back. If you're in my calculus class, we're going to do stuff with logarithms tomorrow, so we'll have more opportunity to review that. But definitely take some time and review your log rules. They come up in a big way in this unit. All right, so 10 raised to this power. And you could actually simplify this further, but that's a different story for a different day, especially because of the clock. All right, but we can look at the picture. All right, I have a regression model. It's like, what picture though? If I go back into my stat plot, I have a graph of L1 against L2, L1 against residuals, but I don't have anything for L1, L3. So I go into my first plot, change my Y list value to L3, so I can look at that scatter plot against this linear equation. All right, so zoom 9. Now it's just a question of, does this look more linear? Right? It definitely doesn't look exponential anymore. Right? Sometimes the equation itself can be distracting, so I'll turn that off. It looks like it's trying to be linear. Right? It's definitely not following that exponential model anymore. Right? So if we take something that has a curved relationship and apply an approach like this, we can straighten it out. All right, and that seems to be what's happening here. It's not perfect, but it's better than it was. This you'd look at and say, this is definitely more linear than the previous iteration of it. All right, but to confirm, we look at our residual plot. All right, so 2, zoom 9, and that looks like a scattering of points. The residual value, when you do L1 against resid, it always compares it to whatever was determined based off of the most recent linear regression computation. So we did stat calc 8 on L1, L3. So it's using that information rather than L1, L2. But this looks like a scattering of points with no discernible pattern. Right? So it's looking like, I mean, you look at this and say a linear regression is appropriate. But be careful, because the linear regression is appropriate for the transformed data set. The transformed data set was exponential, which means exponential is appropriate for the original data set. Right? You got to follow the logic. All right? So the residual plot here applies to the transformed data. What conclusions can we draw from that? Well, we can draw that a conclusion that the linear model is appropriate for the transformed data. That linear model came from an exponential transformation, linear transformation using exponential techniques, which means that the exponential regression would be appropriate for the original data set. All right, so any computations would now be made using this new regression equation, y hat is equal to 10 raised to the blah, blah, blah power. All right. Now, if you want to actually graph this regression equation against the original plot, it's very simple. I don't actually want to graph this. I want to graph 10 raised to that power. So 10 raised to the y1 power. I want my plot, my original plot, to refer now back to the L1, L2. Which is why I'm saying you're going to find yourself going back into different windows, different calculations, doing it over and over again. Zoom 9, alpha, zoom, it won't let me because I locked myself in here, zoom 9. And there you go. All right, so now you have a regression model that is more appropriate to the scatter plot. All right. I'm definitely going to explain this again tomorrow using a different example or two, but that's the gist of it. All right. So